Problem number two here, my warning always right off the bat is to not make this any more complicated than it needs to be. So to get the molecular formula, when you're given one of these structural formulas, is simply count up the number of each type of atom. And so 1, 2, 3, 4, 5, 6, there's 6 carbons and there's 6 hydrogens. That's the molecular formula. Okay, so I just look at the formula, I count up the number of carbons, count up the number of hydrogens. And then to get from a molecular formula to see if it's possible for there to be a simpler empirical formula. And that's just the ratio of elements. And I see that if I divide both of these elements by 6, I get a simpler formula for my empirical formula. It's just CH for that molecule. All right, just have to count carefully here. 1, 2, 3, 4, 5, 6 from the ring, and then one up here. So this one is C7. 1, 2, 3, 4, 5, 6, 7, 8. H8 from my molecular formula. In this case, there's no common factor that I can divide both these by to simplify this. So in that case, the empirical formula is the same as the molecular formula if it cannot be simplified. You also could see this kind of representation. So I had up here just atoms and lines, but you could also have something like this where we're trying to look a little bit more like the real molecule. Again, you just want to do the same thing. Count. There's 1, 2, 3, 4, 5, 6, 7, 8 carbons. And there's 2, 4, 6, 8, 10, 12, 14, 16, 17, 18 hydrogens that's there. Here there is a common factor that I can divide by, so the empirical formula will be simpler. I can divide the carbons and the hydrogens by 2. C4H9. C4H9. And finally we got acetone here. Its molecular formula is C3H6O. And let's see if we can simplify it. Well, we could divide this one by 3 and this one by 3, but we can't divide this by 3. There's just one oxygen, so in this case, C3H6O is also the empirical formula.